Concept 4. Stress-strain curve. Material response to loading is crucial for the design of a structure. Let us consider the response of a typical material such as steel for uniaxial tensile loading. It can be observed that the part of the stress-strain curve is a straight line, which is the elastic region. Beyond the proportional limit, Hooke's law is no more valid. Loading beyond the proportional limit causes yielding. Loading at this point of yielding increases the deformation without any considerable increase in the load. Loading further leads to strain hardening. The stress and strain have a non-linear relationship. It can be observed that the engineering stress-strain curve is misleading, as fracture happens at a stress level below the ultimate tensile strength. This happens because the stress is calculated based on the original cross-sectional area of the specimen, whereas the specimen suffers a good amount of necking, and hence the reduced cross-sectional area must be accounted for developing the stress-strain curve. This can be done by introducing the concept of true stress-strain curve. For materials without a sharp yield point, the yield strength is determined by drawing a line parallel to the elastic part of the curve at 0.2% strain. Wherever this line intercepts the stress-strain curve, we get the approximate value of the yield strength. At certain stress level during tensile testing of the specimen, the elongation of the rod or the plastic yielding is brought about by relative sliding on 45-degree planes. This is manifested as slip bands on the surface of the polished test specimen subjected to tensile loading. These slip bands are approximately at 45 degrees to the load axis. These are also called Luder's lines. This is a permanent deformation which does not return to its original position even after the removal of the load. The Luder lines could also be detected using a special paint called stress coat. It also goes to show that the ductile materials are weak in shear. Mathematically, engineering strain is change in length by original length. If we refer to instantaneous length, say L, then we get true strain. True strain is found by integrating the incremental strain between the original length to the current deformed length, which is given as log to the base E, L2 by L1. Simplifying this, we get log of 1 plus engineering strain, as L2 can also be written as original length L1 plus deformation or change in length. This can be simplified assuming the strain to be small, as L2 square minus L1 square by 2L1 square is also called Green's strain in one dimension, where L1 is the original length and L2 is the current deformed length. This expression of Green's strain further simplifies to engineering strain if the strain is small. Thus, both true strain and Green's strain simplify to engineering strain. Green's strain is used when the strain is small and the component suffers a large rotation, for example, a fishing rod. True strain is used for large deformation. engineering strain is used only when strain is small. Let us now define the material moduli. We define a modulus for each of the following situations: elastic Young's modulus, elastoplastic secant modulus, and plastic tangent modulus. It can be observed that the secant and tangent moduli can vary depending on the point of interest and temperature. However, the Young's modulus for a given material is constant at a given temperature. Further, rate of loading has a considerable effect on ductile materials. In some cases, the yield point is raised. However, the percentage of elongation does not change. Note that in case of long columns, the buckling is governed by Euler's buckling equation, which predicts the critical load for buckling. However, for intermediate columns, buckling happens when the column develops stress greater than the proportional limit stress. In these cases, two approaches are possible. Replace Young's modulus in Euler's critical buckling load equation by either tangent modulus or by reduced modulus. The first one underestimates the buckling capacity and the second one overestimates the buckling capacity. The reduced modulus is given as follows. Toughness can be derived from the stress-strain curve, as the toughness is the energy absorbed by a component elastically, then plastically without fracture. Therefore, the area under the stress-strain curve is a measure of toughness. The area under the elastic part of the stress-strain curve is called the modulus of resilience. For brittle materials, toughness is much smaller compared to ductile materials. The impact toughness and toughness have the difference where the impact toughness is measured under high strain rate of loading using an impact test such as CAE test. Fundamentally, the toughness and fracture toughness are the same. However, toughness is the strain energy the material can absorb without fracture, whereas fracture toughness is the resistance to crack growth that depends on the type of loading. Toughness is expressed in unit Newton meter per meter cube, that is, strain energy per unit volume, whereas fracture toughness is expressed in unit megapascal root meter. Consider an idealized stress-strain curve. The strain at any point on the plastic part of the stress-strain curve would have two components. One, recoverable elastic strain component. 2, permanent plastic strain component. These components could be found by unloading, meaning drawing a line parallel to the elastic part of the stress-strain curve as shown in the figure. The total strain is therefore given by the sum of the two. Consider a hyperelastic stress-strain curve as shown. In this case, when the stretch is significant, a hysteretic loss due to intermolecular viscosity occurs, which is the area contained between the loading and unloading curves. This phenomenon is responsible for rolling loss of tires. As the tires compress and decompress, certain energy is lost due to intermolecular viscosity.